Photoelectric effect. The name itself makes it clear. Photo word is related to light and electric again related to electricity. So current due to light. That's the meaning of photoelectric effect. The experiment was performed by Leonard and Millikan. And I am giving you the experimental setup which was used to observe the effect. These are the two metal plates enclosed in a chamber, evacuated chamber made up of quartz, and here they used a potential divider so that we can apply a potential difference between the two, and I can represent it just by a battery of variable potential. Actually it was a potential divider, so we can use that, we can draw that, or this will also be sufficient. And then a galvanometer, or let me take ammeter. This plate was shined with radiation. So this is a chamber, evacuated chamber. So vacuum inside, two plates. This one was irradiated using radiations, and when the radiations falling onto it have a frequency more than a particular frequency, then we get deflection in the emitter. And now when the experiment was performed, the electron was not discovered, but now we know that the current flowing in metallic wires is always due to flow of electrons. So when there is a deflection in the emitter, it means the electrons are flowing in it. So what might be happening? That when the radiations are falling on those, electrons are emitted, those electrons are captured by this plate, and the electrons start flowing in this. So this effect is called photoelectric effect. So emission of electron from a surface when radiations of appropriate frequency falls onto it. This is called photoelectric effect. The electrons which are emitted, we call them photoelectrons, and the current that flows, we call it photoelectric current. Now there are certain important features of this effect. First, the effect is instantaneous. Instantaneous means there is no time lag. So electrons are emitted as soon as the radiation falls on the plate. Another very important point, existence of threshold frequency. Threshold frequency means this effect is observed only if the frequency of incident radiation is more than a particular frequency. We need a minimum frequency radiation to observe the effect, and that we call as threshold frequency. And two other very important points which I will explain using graph. First I am giving you just the statement and then explain them using graph. The photoelectric current depends on intensity. Not on frequency. of incident radiation. So this current flowing in the circuit and measured by this emitter will change only when we change the intensity of this current. By changing the frequency, the current remains same. Changing intensity and changing frequency means when we are changing the intensity, there is only quantitative change. So we are using same type of more light. That's the meaning of changing the intensity. When you switch on one bulb, then you switch on 2 bulbs, 3 bulbs, 4 bulbs, you are increasing just the intensity. Frequency still remains same. Frequency change means once you are using infrared, then you are using ultraviolet, then you are using visible. In that case, you are varying the frequency. So photoelectric current, it depends only on intensity, not on frequency, and energy of photoelectrons. That depends only on frequency of incident radiation, not on intensity. Very important point from examination point of view also. Current depends on intensity, energy depends on frequency. Okay, now I am giving you 2-3 graphs to explain what is happening here. Very important, all of them. First, the straightforward relationship between intensity and current. This is photoelectric current flowing in the circuit, this is intensity. Linear relationship. You increase the intensity and the current is increasing. Straight graph. Now some more thing. Potential and current. This is the potential applied here and current flowing in the circuit, whatever they. Okay. This is measured by this and V is this. Now if we plot a graph between the voltage applied between the two plates and the current flowing in this. See, when we have a graph like this. Now try to understand the shape of the graph. When we have not applied any potential, see the electrons which are coming here, they are coming with different energies. Some electron may be at the top. Now when we know that there are electrons inside the material, there are a number of free electrons inside the metal, so it is easy to understand what might be happening. When the radiation falls onto this has a lot of electrons, so those electrons, but some of the electrons may be on the surface, some may be well inside the material, some may be inside the material and free, some may not be free, they may be inside the atom. So all electrons getting energy and coming out, so different electrons are coming out with different energies. Those electrons which are spending the minimum, they have the maximum energy, right? So kinetic energy with which they come out, this is different. Okay, now this, what do we call, why do they need energy to come out? See, if this is the surface, one electron, say, moves out, this surface acquires positive charge, so this pulls back this electron. The energy that is needed to overcome this, that is called work function. So you may note it down somewhere. Work function is minimum energy required by an electron to come out. Some electrons may need more than work function because they may be inside. Work function is the energy needed by an electron which is at the top of the surface, ready to leave the surface. Some may be inside, they may need some energy to come up to the surface. Some are inside the atom, they may need some energy to come out of the atom, then they reach up to the surface and then move out of the surface. So those electrons which spend the minimum, which spend only work function, they have the maximum kinetic energy when they are coming out. Okay. So, even when we have not applied the positive potential here, some of them may have enough energy to reach here. So we may get some electrons, some current because of these electrons which are released from this, which are emitted from this and reaching here. So some already reaching. If I start increasing this, more and more electrons are attracted, and this will continue till all the electrons emitted reach here. After that the current is constant. Now we can get current, we can get any change in current only if more electrons are emitted. If 1000 electrons are emitted, then this current will keep on increasing till all those thousands reach here. And once all those have reached, now the current is constant. We need to emit more now to increase it. Okay, this is called saturation current. Saturation current. And if we want to stop, we want that the current should be zero. How can we do? Some electrons are already reaching here, I want to make it zero. So I have to give this plate negative potential so that the electrons are repelled. And so if I give it negative, at some negative potential, current becomes zero. We call it stopping potential. So which stops all the electrons from reaching there, and it is a measure of, very important point, a measure of maximum kinetic energy of electrons. Why? Let us understand, suppose we have a number of electrons. Some electron have 1 electron volt, 2 electron volt, 10 electron volt, and 30 electron volts, and so on, so on. Let us say that the maximum energy that an electron has 30 electron volt. I want to make it zero. So how much should I apply? 30 volt. Because if I apply less than 30, then this electron will reach here. The current cannot become zero. Current will be zero only when I stop even the most energetic electron. So stopping potential is that potential which makes current zero, and it is a measure of maximum kinetic energy of the electron. So this is stopping potential. Okay, now I'm summarizing whatever we have done in this graph. Radiations falling, electrons coming out with different energies. Even when zero, some electrons reach here. When we start increasing positive, more and more electrons reach here. The current is constant. If we make it negative, it starts repelling. When the most energetic electron is also repelled, the current becomes zero. The graph is. So now I hope you can understand the shape of this graph. Okay? What is the meaning of this stopping potential? What is the meaning of saturation current? Saturation current, when all electrons are reaching here. Stopping potential, that potential at which no electron is reaching here. Right? Okay, now to understand last 2 points, what is happening. Current, let me plot 2 graphs for these two, explaining what is the difference when we vary the intensity and then vary the frequency, keeping intensity same. We'll take from here only. Okay, let me draw it again. This is the graph that we are getting. Okay, now let me vary the intensity. Let this one be at intensity I1. Now I increase the intensity of incident radiation. Intensity vary the saturation current. This won't change. The stopping potential will not change. So I2, which is greater than I1, and so on. If I take another one, it may be like this. It is I3 more than I2 more than I1. Another graph when I change the frequency. This is for frequency mu1. Now if I increase the frequency of incident radiation, then this stopping potential, this changes. So if we keep on changing the frequency, stopping potential vary. And this one is at nu1, this is at nu2 greater than nu1. Okay, giving you the idea again very briefly. The effect is instantaneous. As soon as radiation falls, electrons are emitted. There is a threshold frequency. You will get this only when the frequency is more than a particular frequency. If you vary intensity, current will change, but energy remains same, energy of photoelectron. If you vary the frequency, then the energy will change, current will not change, photoelectric current will not change. Now, why is this happening? See, when these observations were made, radiations were supposed to have wave nature. Wave nature means we have done the wave nature of light. That wave move forward in the form of wavefront and energy is distributed on the entire wavefront. So let me try to explain it using wave theory of light. So what is happening? The radiation is coming, it's in the form of wavefront, is striking this surface. Now whenever a wavefront interacts with the surface, the energy is transferred from the wave to the surface, and this is never instantaneous. It depends on the time for which the surface is exposed to radiation. If the surface is exposed to radiation for longer time, more energy will be transferred, and for short duration, less energy will be transferred. And electron may take even minutes or hours to come out of the surface. It comes out when it receives sufficient amount of energy needed to come out. So it means the effect is instantaneous, and the existence of threshold, they cannot be explained using wave nature, because there is no question of threshold when we are saying that even a weak radiation can cause the emission of electron if it is allowed to fall or interact with the surface for a longer time. So radiations of higher frequency, they can cause emission quickly. Radiations of weaker frequency may take longer time. So it will depend on that. And it is never instantaneous. And further, last 2 points. In wave, the energy is distributed on the entire wavefront. So it is transferred to the surface. When we increase the intensity, or when we increase the frequency, when we increase the energy of the incident radiation, then even intensity will increase. How we define intensity? Energy per unit area per unit time. In waves we define it like this. So again those 2 points can also not be explained. We can change, when we change the intensity, it means energy is increasing. So those 2 points can also not be explained if we consider radiations just like waves. Now, this was explained by Einstein. He explained using Planck's particle nature of radiation. So it means we cannot explain photoelectric effect. This couldn't be explained by considering light as a wave. So that's why that another nature for radiation basically came into line. That is particle nature. So radiation also have particle nature, but this nature is different from the nature that materialistic particles show, in the sense that the bodies that we see in day-to-day life, particles, they have a definite position, they have a definite mass and velocity, something like that, okay? But when we are saying particle nature of radiation, it simply means that when radiations interact with the surface, then the energy transaction is not continuous, which means the energy is transferred from wave to the surface only in steps of energy. That is, say, for example, if I say X, so when the radiation is falling onto the surface, it transfers energy X or 2X or 3X or 4X. It can never be 1.1X. It can never be 2 by 3X. And that X here is called photon. So photon is a packet of energy. Photon, packet of energy. We cannot say that light is made up of particles, materialistic particles having some mass. No. It simply means when the light radiations interact with the surface, the transfer of energy is in steps of h nu. That's it. So if nu is the frequency of radiation, h is Planck's constant, so the energy transfer will be in multiples of it. This we call quanta of radiation, and this is photon actually. So E is equal to h nu, this is the energy of photon, or in terms of wavelength we can write it as c by lambda. Even the momentum is defined as E upon c. E is equal to mc square, it will come from there. E is equal to mc square, which can be written as mc into c. This is momentum. So now we can consider this particle nature of light and try to explain what is happening in photoelectric effect. When radiations are falling, transfer of energy is, we can take this as interaction between photon and electron. So one photon having energy h nu is giving its energy to electron. Here the energy is given to electron and electron moves out. So electron use this energy in two ways. H nu is the energy received. This is simply the conservation of energy. H nu energy the photon has, it transfers all its energy to the electron. A sort of collision is there. Photon giving all its energy to, so radiation is giving energy h nu, transfers it to one electron. Electron uses it in two ways. In coming out, kinetic energy plus the energy that is needed to come out. Energy spent to come out. This is how the electron is using this energy. Now, different electrons are using different energy to come out. As I told you, because some are well inside the material, some are on the top of it. So, some of them absorbing all energy but are not able to come out. They remain inside, and some of them come out. So, we shall be writing this expression. It can be written in terms of fixed quantities only if we have definite quantities actually. This is a range. Energy needed to come out is, required energy to come out by the electron is different. So let me concentrate on that electron which is needing minimum to come out, that we call work function. And in that case, this kinetic energy will become maximum. Which electron has maximum kinetic energy? The one which is spending minimum to come out. Okay. So this is the simply conservation of energy. Energy of the photon, energy taken by photon and is spent in two ways. Coming out and retained the remaining as its kinetic energy. Or I can write it as c by lambda is equal to k max plus w. Okay, now let us try to explain all those four features using it. The effect is instantaneous. It's a collision. All collisions are instantaneous. The energy is transferred by photon to the electron, it receives its energy and come out. First point solved. Second, existence of threshold. Now imagine if the incident is less than W, no electron will come out. Electrons may come out only when the energy of incident photon is more than the work function. And when it is just equal to the work function, that is what we call threshold. So H nu naught, if this is the minimum that is needed, is equal to W. So nu naught is threshold frequency. Threshold frequency is that frequency for which the energy of the incident photon is just equal to the work function. So now I can write this as H nu is K max plus H nu naught, or K max is H nu minus nu naught. Just keep in mind one expression, others I am just substituting or taking them left right. But important observation from this graph. If I plot a graph between frequency and kinetic energy, it's a straight line graph, right? And we'll start from here. Nu naught. If nu is equal to nu naught, kinetic energy is 0. So it will start from here. And I can take it here. So this graph is also very important and we may use it. What is the slope of this graph? Any 2 points I can take and then find out the slope. Kinetic energy divided by nu minus nu naught. Let me take 1 point, okay? Here. Let us say the kinetic energy has some value at frequency nu, and this is nu naught, this is 0. So kinetic energy minus 0 divided by nu minus nu naught. This is the slope. And what is this? Equal to h. So it means if I draw this graph for different materials, the slope will remain same. The slope of this graph is the Planck's constant. Okay. Sometimes in exams you are given that the graph is written in terms of stopping potential. I told you that the stopping potential is, this is K max. The stopping potential is the measure of maximum kinetic energy. So if the stopping potential is V, what is the maximum kinetic energy? EV. How do we calculate? Q into V is kinetic energy. Okay. So stopping potential in terms of that, it is actually EVS. Kinetic energy can be written in terms of EVS. So if I write it, EVS is H nu minus nu naught. Then Vs is H upon E, nu minus nu naught. So in that case, the slope will be H upon E. So if a graph is plotted between a stopping potential and nu, the slope is H upon V. If the graph is between kinetic energy and nu, the slope is H, but the slope is constant. So this expression can also be written in terms of threshold wavelength. Nothing new in that expression actually. We have already covered everything now. K max is H nu minus nu naught. It can be written in terms of threshold wavelength. So C can be taken common. Different variants of the same expression actually in terms of lambda, in terms of frequency, but you have to keep in mind the initial expression. H nu is equal to K max plus W. That's it. And W is H nu naught. So that's all in this topic of photoelectric effect. Thank you.